Then license assisted access is that basically it's also called unlicensed access. So there is so much of unlicensed means, actually I want to call it license exempt band, like 5.8 gigahertz, 2.4 gigahertz. Why don't we grab that and use it for LTE? Right? Not for Wi-Fi. Use Wi-Fi band for LTE. All right, so this is a different way of integrating. Basically, get all the unlicensed stuff. Obviously, if you take unlicensed stuff, you're not guaranteed somebody else may start their transmitter and you're gone. Right? It is not guaranteed to you. So this will be used mostly for complementary band. If I have two bands, I have this tiny band which I have bought, and this big band which I haven't bought. I will combine them. Most of the time, people will get good service, and when the complementary band is not available, you get some service. And this will be particularly used in public hotspots and in buildings. And there are rules in different countries. In some countries, some of these 5 gigahertz bands are used for radar and things like that. And so this is basically different between this and the Wi-Fi thing is that in this case end-to-end LTE. The mobile knows all the signals that they're getting in the millisecond frames and things like that. In the case of Wi-Fi, basically we are connected to some machine which translates the two protocols. Right? Here there's no translation, LTE to LTE. Everything is LTE. Right? And these are the bands. And there are different rules in different countries, different bands, but that is LTE-U, also known as LAA. Multimode base stations. So now, base station, mobiles are already multimode. My phone does 2G, 3G, 4G, Wi-Fi. Doesn't do WiMAX, but does Bluetooth. But the base stations don't. They don't do Wi-Fi for sure. They do 2G, 3G maybe, but they don't do Wi-Fi. They're saying, why not? Let's do everything. Okay, whatever is best, they'll do it. Okay. So the main processor, what do you do how do you process all these different bands? Something is running at 5 gigahertz, something is running at 700 megahertz. So then it is important to understand this one. Okay, so just listen carefully. Basically, what they do is when they have something coming in, they pass it through, they amplify it first, they receive signal. Then they do A to D conversion. And then they do intermediate frequency processing. So this is very high frequency. They bring it down to some frequency where we can process it. And that is called IF, intermediate frequency. And then they bring it down to the real frequency band, that 20 megahertz means they become 0 to 20 megahertz. And then we do the baseband processing. Okay? So we have very high frequency, which is 3 gigahertz or 5 gigahertz or something. Right? 20 megahertz over there. We bring it down to intermediate frequency, bring it down to the earth so you can look at it, and then bring it down further to 20 megahertz. Baseband. So I'm just trying to understand two words, IF and baseband. And so you need software-defined radios. So these are called SDRs because what they do is they use DSPs, digital signal processing. Okay, these are generally what you call FPGAs or the field programmable gate arrays, and they can sample the signal at a very high speed and then figure out what frequency it is. You know, normally we know the frequency, so we put the filter and we do all the processing depending on the frequency. In this case, we don't know the frequency, so and right this second I'm processing this band, next second I'm processing this band, next second I'm processing that band. Who knows? This is a multi-mode, right? And therefore, we have to process all the bands. So we do all of that in the software. In the hardware, we do a sampling at a very high frequency. Okay. So SDR, so two terms. SDR, PA is the power amplifier. LNA is the low noise amplifier. DAC is the digital to analog converter. A3C is the analog digital conversion. IF is intermediate frequency, and B is broadband. Baseband. Okay. Now the reason this is important to understand is because this leads us to the second thing which will come up later. Yeah, go ahead. Okay, so we know the frequency. I'm sorry. I should say, if I am processing Wi-Fi, I know that I'm going to get 5.8 gigahertz. Except that what I'm saying is, I may have to switch to 2.4 gigahertz in a second because I'm talking to B station. and I may have to switch to 900 because I'm talking to 3G station or something, right? So we know the frequency, but it could be any frequency. So the point is that all of this here thing, in the radio, the analog parts are very expensive. They consume the most money and most power as well, okay, and the most problem. So D to A converter, A to D converter, and these two amplifiers, they are the expensive part of it. Now, if he's saying that even the circulator is expensive part of it, oscillator, this one, yeah. So basically, I didn't explain the oscillator. What it is this oscillator produces a signal so that basically subtracts out the frequency. So this one, so if you want to bring it down from there to here, you take the difference frequency and inject that in, so the frequency comes down. And even that is expensive. So the analog parts we want to do minimum. So now we go back to intelligent multi-mode RAS selection. Now, if you are going to speak everything, then we have to decide which one to speak at what time, right? So if you just dumbly select which is what it is run right now, in your Windows, then it selects between wireless and wired. It just selects because the speed of one is higher than the other. Okay, but it doesn't know that the higher speed network is loaded, right? So intelligent means you have to know the load, you have to know other things, cost, and everything else. Based upon that, there will be a policy, there will be an algorithm which will let you decide whether to take 2G, 3G, 4G, 5G, Wi-Fi, Bluetooth, whatnot.